So finding the general solution to the differential equation, first thing we're going to do is solve for the differential, which is dy. So finding that general solution to dy dx is equal to 2x. Get the dy by itself, so we have dy is equal to 2x dx. And then we're going to antiderive both sides of the equation. So antideriving both sides, antideriving dy is just y, antideriving 2x is x squared plus c. And that's the general solution to the differential equation. Example 2, finding the general solution to dy dx is equal to cosine of x e to the sine x. Get the differential by itself, so dy is equal to cosine of x e to the sine x dx. Antiderive both sides, so we get y is equal to, we'll need to use u substitution to antiderive. Let u is equal to sine x, then du is equal to cosine x dx. So cosine x dx gets replaced with du, and sine x gets replaced with u, so we have the antiderivative of e to the u du. Antideriving, we get y is equal to e to the u plus c. Replacing in u, so e to the sine x plus c is the solution to our differential equation. Finding the general solution to dy dt is equal to 1 over 1 minus 2t. Get dy by itself, so dy is equal to 1 over 1 minus 2t dt. Antiderive both sides, so y is equal to, we'll need to use u substitution again. So u is equal to 1 minus 2t. Du is equal to negative 2 dt. Getting dt by itself, so that's negative 1 half du. Replacing in 1 minus 2t with u, so we have 1 over u, and replacing dt with negative 1 half du, taking out the coefficient of negative 1 half, then antideriving 1 over u, so we have negative 1 half natural log of the absolute value of u plus c, replacing in the value of u, so we have y is equal to negative 1 half natural log of the absolute value of 1 minus 2t plus c. So now we're going to find particular solutions to the differential equations. To find the particular solution to the differential equation, or to solve the initial value problem explicitly, we're going to do the same thing where we solve for the differential, and we're going to antiderive both sides of the equation. Solving for the differential, we get dy is equal to 2x dx. Antideriving both sides, so we get y is equal to x squared plus c. But now we're looking for a particular solution, so we'll sub in the given values to solve for c. Given x is 1 and y is 3, so we have 3 is equal to 1 squared plus c, so c is equal to 2. So write the solution with that particular value of c. So we have y is equal to x squared plus 2 is the particular solution. And y equals x squared plus c is that general solution, and the y equals x squared plus 2 is the particular solution. Next example, we're going to solve the differential equation with the initial value. So getting the differential by itself, dy is equal to cosine of x minus 3x squared dx. Antideriving both sides, get y is equal to sine of x minus x cubed plus c. Using the initial value of y is equal to 3 and x is equal to 0, we get 3 is equal to sine of 0 minus 0 cubed plus c, so c is equal to 3. Then back to the general solution, replacing in the value of c to get the particular solution, so y is equal to sine of x minus x cubed plus 3 is the solution to the differential equation. Find our solution to the differential equation with the initial values given. So getting the differential dA is equal to cosine of t sine of t dt. Antideriving both sides, we get a is equal to, needing to use u substitution to antiderive, so let u equal sine t. Du is equal to cosine t dt. Cosine t dt is in the problem, so that's du. Sine of t is u. We're going to antiderive u du. So that's 1 half u squared plus c. So a is equal to 1 half sine of t squared plus c. And then replacing in the initial value, a is equal to 3 halves and t is equal to pi over 2. So 3 halves is equal to 1 half sine of pi over 2 squared plus c. Sine of pi squared is 1. So 3 halves is equal to 1 half plus c, so c is equal to 1. And then writing the particular solution, a is equal to 1 half sine squared t plus 1.